2016 called A New Kind of Trade-off. And what he shows there, he introduces this kind of trade-off where you actually have, if you see there, you have an upper bound that goes beyond worst case. But more interestingly, you have an infeasible region that goes beyond the worst case. So what kind of problems, what kind of measures could actually have this kind of trade-off? Right. So what we were interested in particular was understanding, do monotone circuits, so when I don't have the NOT gates, do they have this kind of supercritical trade-offs in terms of size and depth? Can depth go beyond linear? And there were some earlier supercritical results before this name was actually introduced. So these are prior to Rozborov's paper. Okay, so this question, which we'll talk about today, is do these supercritical trade-offs exist? And we know that non-supercritical trade-offs exist. So we do know in the particular case of monotone circuits, we have very extreme examples. So we know that there are circuits that are, there are functions which have linear monotone circuits, so as small as it gets, but any monotone circuit requires depth which is almost linear, n over polylog. So we know we cannot balance them, but what we're asking here is, okay, maybe I can't balance completely a circuit, but can I at least say that if I have a circuit of size S, I'll have another one of more or less the same size and depth, which is at most n, so that it won't go beyond like this worst case depth. Is this possible? Okay. Are there any questions about the setup? Yes.
Why is it called supercritical, and what's the difference really between?
Okay, that's a great question. Okay, so we have this worst case bound, which is just what would the trivial circuit or the trivial algorithm do? In this case, circuit. The trivial circuit would have depth n. So is it possible to get a lower bound where there do exist small circuits, but they would require depth larger than this worst case? So larger than n, superlinear depth, for example. So that would be supercritical. Yes. Yes. So if we're talking about monotone formulas, if there is a formula of size S, we can construct another formula that has depth O of log S. So it's like we do this balancing of the formula. This is not possible for circuits. So there might be a circuit of size S, but no circuit of, if I'm talking about constant Fanon of logarithmic size, logarithmic depth, sorry. So here what I'm asking is, okay, maybe not logarithmic depth, but can I at least get the depth down to n? Yes. Yes, if you have a constant Fanon. Yes. N is the number of inputs. Yes. Yes, number of inputs. Okay. So in order to explain why we could perhaps expect there to be such trade-offs, I'm going to tell a few stories. So first, the story of perfect matching, which is actually the monotone story of perfect matching. So just to be concrete, I'll be talking about bipartite graphs. So G is a bipartite graph and vertices on each side. And this is just the function. I'm writing it out for a reason. It'll come up later. So I want to know, is there a subset of edges such that every vertex has degree exactly 1 in this subset? Okay, that's the bipartite perfect matching function. And for example, for this graph here, we can see this whole set there shows that there is no perfect matching. Okay, so and just this is a monotone function with n squared. So contradicting what I just said, in this particular case, I have n squared variables. All right, so what do we know about the complexity of this function for monotone circuits? So we know there are monotone circuits of size 2 to the n. These are actually even monotone formulas of size 2 to the n. And the first superpolynomial size lower bound for monotone circuits, shown by Rozborov in the 80s, was for the matching function. So he showed an n to the log n lower bound. Then some years later, Raz and Victorson showed a monotone circuit depth lower bound of n. So this shows that for formulas, we know the complexity. It's really 2 to the n. But since then, there has not been much progress. So it's been 30 years, and we still don't know what is the complexity of matching for monotone circuits. And we can compare this with another result that was in Rozborov's paper in 85. He showed superpolynomial lower bounds not only for matching, but also for the clique function. And for the clique function, he also showed n to the log n lower bounds. But just a few years later, Alon Bopanna improved this to exponential lower bounds. Again, there were depth lower bounds, and these can even be exactly matching the formula size, which is just looking at all subsets of size k. So you can get the exact depth. So for formulas, again, it's very tight. But for circuits here, we actually have exponential lower bounds, but not for matching. So what's happening here? What is the complexity of matching? Is it the case that there are no circuits of size 2 to the little o of n? And if so, why can't we prove this lower bound? Why can't we prove exponential lower bound? Or is it the case that there maybe are circuits of size n to the log n, but we can't find them? And why can't we find them? Okay. So one theory is that maybe we can't prove lower bounds because they're not true. And we can't find these circuits of size n to the log n because they look so different. So we're not used to seeing circuits like this. So could it be the case that there are circuits of size n to the log n, but they actually have depth n to the log n? So they're not something we would easily come up with. Yes. N. So there's a matching upper and lower bound of depth n. Yes. Yes. So we know, yeah, if we know already, if there were to be a circuits of size n to the log n, it would be deep, at least depth n. But could it be the case that it has depth n to the log n? Okay. Okay, there's another problem which is I want to talk about, which is not talked so often, is odd factor. And now you see why I wanted to write the bipartite perfect matching function, because the odd factor function is very similar. So I'm asking, is there a subset of edges such that every vertex has odd degree in the set? Okay, so instead of degree 1, is there a set where every vertex has odd degree? So if we look at this same graph here, it actually does have an odd factor. It doesn't have a matching, but it has an odd factor. And now the story of odd factor is exactly the same as perfect matching. We have the same lower bounds and the same upper bounds. Okay, the proof just goes through in this exact same way for odd factor. One interesting thing about odd factor is that it's somewhat easier than matching. It's complete for log space. So again, we could ask the same question for odd factor. And maybe since it's an easier function, it might be easier to find these circuits. Okay, and another reason to bring up this function, odd factor, is because of the Satan formula. So the Satan formula, we're given a graph. We have labels on the vertices of the graphs, so 0, 1s. And we have variables on the edges. So for example, there I just wrote some of the 3 of the variables. And for every vertex, we have a constraint that says that the sum of the variables that are adjacent to that vertex is equal to the label mod 2. Okay, so in this case here, I would have x plus y plus z equals 1, 2, which would translate into some clauses if I want to write this in CNF form. Okay. So I don't know if you see already some relation between this and odd factor. But if you have all the labels 1, then the Satan formula over this graph is true if and only if this graph has an odd factor. Okay. So Satan formulas appear a lot in proof complexity. So I want to talk about some results in proof complexity. So I have to introduce some proof systems. So we've seen some of these already. So resolution, we've just seen. So we have a CNF formula and we can apply the resolution rule. And we want to derive the empty clause to show that something is unsatisfiable. Okay. For another proof that we're going to be interested in are going to be for cutting planes. So here, instead of clauses, we can write it as linear inequalities. And we're going to apply rules that are sound over integers. We also include the inequality that the variable is between 0 and 1. And then we do reasoning over integers. So we can take linear combination, we can take division and rounding. It won't be very important exactly what the rules are. But it's a sound proof system over integers using linear inequalities. And for these proof systems, I can write them as DAGs, where the nodes are labeled by the line in the proof, and I have a derivation step to derive the parents of the 2 children using some rule in the system. Okay, and again, I can have the same kind of complexity measures I had for circuits. I can talk about size, I can talk about depth. I can also, in the case of resolution, talk about the width of the clause, which is the max or the width of the proof. The width of the clause is the number of literals in the clause, and the width of the proof, the maximum number of literals in any clause appearing in the proof. Okay, this will come up later. Okay, and again, for these proof systems, I'm going to have the same kind of trivial upper bound I had for circuits. There are always these proofs of exponential size and depth n. So this would be just a tree where I just look at every variable and consider whether it's true or false. Okay, so going back to the story of these Satan formulas. So these were actually introduced by Satan in '68, and they were used to show the first proof complexity lower bounds. And they were also formulas that were like the first ones, one of the first ones that were proven to be exponentially hard for resolution. And then subsequently, there were other proof systems for which this was shown to be hard, like sum of squares, bounded depth Frege. It was actually a very important formula in proof complexity. And it was a long-standing conjecture to show that these were exponentially hard for cutting planes. Because linear inequalities doesn't seem like they can actually reason about parities. And this was open for a long time. There was not any progress in proving these lower bounds. Until, actually, quite surprisingly, there was this upper bound shown a few years ago that there are quasi-polynomial size cutting planes proof for Satan. So linear inequalities can, in some sense, reason about parity. And what was interesting about this upper bound is that these proofs actually have depth n to the log n. So this also gives some reason why perhaps we could expect these things to exist. That maybe the small proofs are can be very long, very deep, sorry. And perhaps that's why we couldn't find this upper bound before, because they were in some sense unnatural. So could the same thing be happening with perfect matching? Later on, it was also shown that any cutting planes refutation actually does require linear depth. So again, there's some similarity there. But we still don't know is, can it be the case that that any n to the log n proof does require depth n to the log n? Yes.
Basic question. For the set-in formula, what is the graph on which it is defined?
Good question. So there are some graphs which are easy and some graphs which are hard. So hard graphs would be like expander graph, for example, or if we have a grid graph, n by n grid graph would be hard. Are there other questions? Okay. So the question we're interested in here are, do supercritical trade-offs actually exist in proof and circuit complexity? Do these appear at all? If we expect them to be, or conjecture them to be true for perfect matching for Satan, a first question is, are they true for any function, for any formula? Okay, so what we show here is that for monotone circuits, this actually is the case. There are functions that have this kind of supercritical trade-off. So they have small circuits, but any small circuit will require super polynomial depth. Okay, so we do know that this kind of trade-offs do appear. But we still don't know if matching is one of these functions. This is still open. Okay. And then in proof complexity, there were already some results showing this supercritical behaviors for proofs. So there were formulas that have small resolution proofs, but any small resolution proof will have really, really large depth, also for cutting planes. But these were not completely satisfactory because the size of this formula was super large. So the depth was not really supercritical in terms of the size of the formula, the number of clauses in the formula. We introduced this notation. It wasn't truly supercritical. It wasn't supercritical in the input size. And it doesn't quite capture Satan, the Satan upper bound, where it is actually supercritical in the size of the formula. So what we also showed here is that there are formulas that exhibit this truly supercritical trade-off, which is in terms of the size of, in terms of the input size. And this also holds for both the resolution and cutting planes. And then again, we still don't know whether Satan is one of these formulas. Okay. Yes. They are constructive, but they're not for these formulas in particular. So I will explain a little bit where these come from now. Yes, so the size is super polynomial. It's small, but it's like n to some polylog or something. S is not polynomial. No. S is super polynomial. It's a little bit more. Yeah, it's a good question. Okay. So this is what the proof looks like. So there are two steps. In the first step, we will show a supercritical width depth trade-off for resolution. So I'll state it in a second, and then we'll show how width depth trade-offs for resolution implies these size depth trade-offs. Okay. So the width depth trade-off is of this form. So we'll show that there is a resolution, there's a formula that has a resolution refutation of width W. So every quadruped in the proof has at most W literals. But if I'm below a little bit more than W, so let's say W plus square root W, then the depth has to be super polynomial in the size of the formula. Okay, so it's this trade-off between the width and the depth. And then for the second part, we show in a black box manner. These are called lifting theorems, where we can show that we can, from this width depth, we're going to get a size depth. So we're going to prove it in the other direction. So suppose I had a small size, small depth monotone circuit computing some function, then I'm going to get a small width, small depth resolution proof. And if I showed that this small width, small depth did not exist, then that means that the small size, small depth does not exist. Yes. That's a good question. So it can be from constant, in which case the depth will be polynomial, or it can be up to I think up to polylog. Yes. So Rezende proved width depth trade-off, and another one I'll talk about later, but it wasn't super polynomial in the size of the formula. It was only super polynomial in the number of variables. And I'll get to this in a few slides, but because of this, we could not get monotone circuit trade-offs because it wasn't super polynomial in the formula side.
But you need this plus square root W, like why is that not good enough, but it's less than W implies it's polynomial. So that's also with that trade-off, right?
Wait, so can you say that again?
So if you just have the theorem that but for width less than W, it implies super polynomial.
Right.
That's also width depth trade-off. Why do you have this W plus square root W?
Yeah, it's just giving you a little bit of margin, even if you go a little bit above the minimum width. So you can do it in width W, but even if you go a little bit above, that doesn't help you yet. You need to go like more than that, above width. You do need in order to get these, you do need a little gap. Yeah, if it were too small, you wouldn't be able to get anything for size depth. Yeah. Okay, so for the first step, I'm going to explain where this comes from. And for this, I need to introduce a game. Maybe you've seen this before. These are called the cop robber games. So it's defined on the graph. In our case, we'll be interested in these like long, skinny grids. They're actually cylinders. You have these wraparound edges. And you have one robber, which is somewhere in the graph, and you have a number of cops, let's say W cops. So there you have the robber, you have some cops, and the game proceeds in rounds. So at every round, one cop gets into the helicopter and he signals a vertex where he gets out of the graph, gets in a helicopter, signals a vertex where he's going to land. Before he lands, the robber moves. So he's very fast, he just moves through the edges, but he has to avoid all the cops. And then the cop lands on the signaled vertex. Okay? And the game ends when the cop lands on the robber, catches the robber. Okay, so let's see an example. So here that last cop there got onto the helicopter. Now he signals he wants to catch the robber, so he signals he's going to like land there. But of course the robber is smart and he's going to leave. So he very fast goes to the other side. And if you didn't like see, there's a path there. You can go there avoiding all the cops. So after he does that, then the cop actually lands there and the robber's gone. So this is the game. And we're interested in two measures, how many cops and how many rounds. Okay. So what is the minimum number of cops needed to catch the robber in such a grid? Two K? 2K? K plus one? K plus one? Okay, yeah, you can do it with K plus one. Because you can have K cops and just go walking with them, sliding until you catch the robber, moving one at a time. Okay, but how many rounds would that take if I want to do it with K plus one? Basically L, right? I'm going to have to go through the whole sweeping the graph. Okay, but if I want to minimize the rounds, if I want to be really fast, how many cops do I need? L would be, I could do, I mean, I still have to place each cop one at a time. How many rounds would I need in that case? I have to, the cops can only go one at a time. So I need at least K rounds to just put them to somewhere, K of them. Log L, yeah. So I can do a binary search here. And then in that case, I actually only need 3K. I don't even need L, I just need 3K because I have to be able to do this binary search. And then in basically log L rounds, I can catch the robber. Okay. And then can I do anything in between? Anything like intermediate between 3K and K? This one is a bit trickier. I think you have to think about it at a time, but you can actually do something in between. So if you have 2K plus one, you can do square root L. But if you have less than 2 times K, then you actually need L routes. Okay. Okay, so we can play this game. It's fun. But this actually relates to width and depth and resolution. So the number of cops is basically the resolution width of the Satan formula on this graph, and the number of rounds is resolution depth. Okay, so here we've just kind of argued. Where? Oh, yes. With tree depth and tree width of the graph, you mean, right? There are connections between the tree width of the graph and definitely regular resolution. So special subclass of resolution. I think there might also be for resolution, but I don't know if it's tight. But there is an intuition there that I can cut, right? With where looking at the tree decomposition. So I think the upper bound definitely holds. Okay, so we just argued here a kind of trade-off between both measures, between the width and the depth, between the number of rounds and the number of cops. So this would give a width-depth trade-off for Satan for resolution, but it's not super critical, right? It's a normal trade-off. So in order to make a normal trade-off super critical, Rozborov introduced this hardness condensation, where he takes this medium hard problem over some inputs 1 through n, and then compresses it into this 1 through m, where m is much smaller than n, in a way that hardness is preserved. Okay, so the way one way of doing this is looking at, we have XOR of we have an expander graph here, and we consider some y variables, and we substitute the x by an XOR of y variables. And now we reduce the number of variables, and if we can make sure that the hardness is still there, we now have hardness in terms of much fewer variables. Okay, so this is a way of like condensing the hardness. This was used in several other works, but the problem is that now the number of clauses I need to write this formula actually blows up. That's why I get these truly supercritical results. Okay, so we have to do something different. And this was a technique introduced last year, where instead of having these gadgets, we actually substitute the variable directly by one of the variables. But again, we have to do this in a smart way so that we actually preserve hardness. So how do we do this in the case of the, yes?
Gadget used for in the last slide, what was hardness condensation used for?
So we want to reduce the number of variables so that our trade-off, there was a normal trade-off. We want it to be supercritical. Okay, so we need to reduce the number of variables. So before it was just giving something which was a depth which was smaller than n. But if we make sure the variables get much smaller, then this depth now is like larger than the number of variables. So it becomes a supercritical trade-off. Okay. And in this case, I'm not using the gadget, but it's like substituting directly. Okay, so in the case of our grid graph, what Grohelichte, Noyen, and Schweitzer showed last year was that it's a very ingenious way of identifying variables. So I won't get into too many details here, but there are, you choose some numbers, these numbers mi, different number for each row, and you're going to identify the nodes in that row that are equivalent modulo this mi. So for example, those on the top, those purple vertices would be identified. And you would identify the adjacent edges. So the left, right, up, down edges would be identified. So let's zoom into like 2 layers of this graph. So this would be like 2 layers. And once you do this identification, you're going to have this like collapse into a much smaller set of constraints and set of variables. Okay. So just to have some idea of what's going on. Okay, so we started with that graph, and then we were able to condense it. So the size becomes much smaller. Yes. The 30 there was the L. Yes, and we're just looking at what happens between 2 rows there. And there's some identification which gives this coloring, and that's what later reduces the size. So the size becomes much smaller, but now we have to analyze the cop rubber game in this this compressed graph, where now, since we identified things, once you one cop lands one vertex, he's actually on several different vertices at the same time. So he has like these clones all over the graph. So if you chose this identification in a very smart way, these clones will be placed in such a way where it won't really help the cops catch the robber. So that's what you have to show. So that this hardness is still preserved. And what we needed to do was get a stronger version, because in their result, they only, what Sumega asked, they only had a gap of 1 between the width and the lower bound that they could get. And we needed a larger gap in order to be able to get the size depth lower bound. Okay, so that's all I'm going to say about the first part. And then how much time should I? Oh, okay. So for the second part, how do we get from the width depth trade-off to the size depth trade-off? Okay. So there's this crucial tool that was well introduced originally in the 90s, but for formulas for tree-like objects, and in 2018 was introduced for circuits, DAG-like objects. So these are called lifting theorems. And the idea here is that we are going to start with the CNF formula and some large enough integer m, and we're going to construct a function based on these that satisfies this property that we saw before. So if there is a small size, small depth monotone circuit computing this function, I'm going to be able to look at that circuit and extract, going like node by node, I'm going to extract a small width, small depth resolution proof for the formula F I started with. Okay. And this is this result that was showed in 2018, and it's been used a lot for obtaining. Usually without the depth requirement, they just noted the width to size. But if you look at the proof, you actually get this this depth too. And there is one catch here, which is that the number of variables of the function constructed is proportional to the number of clauses in the formula. So that's why the width depth trade-offs that were only supercritical in terms of the number of variables and not on the number of clauses did not give anything when we used this lifting theorem. Okay. So in our case, we already have a truly supercritical width depth trade-off. The only problem was that there are some hidden constants there, and we're playing between this k. 3 times k is already too much, right? 3 times k, we can do this very fast log strategy, number of rounds. So constants here, we really need to know what they are. Like they cannot be, they have to be smaller than 2. So this seems at first a little bit challenging. So ideally, we would like no constants, right? So we would like to say, okay, if I have size m to the w, depth d, I'm going to get width w, depth d. This would be our dream result. So since at first it seemed a bit hard, we decided, okay, let's try to get this for resolution. So let's try to get, instead of getting a function there for monotone circuits, let's get another formula for which we can get size depth trade-offs for resolution. And we actually were able to show pretty tight size depth lifting from width depth for resolution. So it's except for the factor 2 there, it's tight. And the proof turned out to be surprisingly simple. There's a technique we use a lot, random restrictions, and it worked with random restrictions, except we couldn't use the usual gadget that we used. We had to compose it with another function, but it's a pretty, I could present the proof if I had 5 more minutes. I think it would be possible. And so using this, we are able to get supercritical size depth trade-offs for resolution. So this was the first step. But then, okay, we wanted to get this for monotone circuits. This proof is a lot more complicated, so I won't be able to explain more, but just to say that we cannot actually get something which is also close to optimal. So you lose now a factor in the exponent, but it's close to optimal. And then we get the same kind of the size step trade-off for monotone circuits. And the same thing holds for cutting planes. So the same result for monotone circuits, same kind of lifting theorem holds for cutting planes. Okay. So, and one more result I wanted to mention, which does not fall into size depth trade-offs. This is another kind of trade-off. But this is one of the trade-offs that Razborov showed in his original paper in 2016, was a trade-off between size and width for tree-like resolution. So he showed some formulas where if I wanted to optimize the width, the size of the resolution proof became doubly exponential in the number of variables. But again, the size of the formula was already exponentially large. So it wasn't supercritical in terms of the size of the formula. So we obtained this size width trade-off, which is supercritical in terms of the size of the formula. And the way we obtained this was, again, from the base result, which was the width depth trade-off. We showed this lifting theorem, So it's a black box lifting theorem. So you can apply it also if you get a different depth width trade-off. You can apply the same this lifting theorem, and you'll get that result for different parameters. If you get a better depth width trade-off, for example, it's a black box lifting. Okay, so those are the results. And then I wanted to mention another paper that came out at the same time as ours, who also obtained size depth trade-offs. So this is a work by Grossmeister, Ries, and Sokolov. So they also obtained these supercritical size depth trade-offs for the same type that we have for monotone circuits and for cutting planes. And the overall strategy is very similar. They have a depth width trade-off and they apply lifting, although in their case, they can apply lifting as a black box because they have they're more robust, so they don't care so much about the constants. And it's a very nice paper. They have the formula that they have is more natural. It came from studying something in the TFNP hierarchy. But the depth width trade-off is very different. It's a very different proof. And they get different parameter regimes. But morally, it's the same message that we actually do have these trade-offs for monotone circuits. And one thing I did not mention here is that our trade-off also gives some results for the Weisbeider-Lehmann algorithm in terms of the dimension and the number of iterations. So you get more robust trade-offs there. Okay, so yeah, just to wrap up. So yeah, what we showed here were these monotone that monotone circuits exhibit this kind of supercritical size depth trade-off. And also in proof complexity, we also have these in terms of number of clauses, not only number of variables. I mentioned also that for tree-like resolution, we can get this supercritical size width trade-off, and that you can get more robust Weisbeider-Lehmann trade-offs. And I wanted to finish with some open problems. So I guess for me, the main open problems are understanding the complexity of perfect matching and odd factor, and the complexity of Satan for cutting planes. So I think these are great problems, and I think we should solve them soon. And then another question is, it seems there are so many connections between these problems. Are these just coincidence, or can we make these connections formal between odd factor and Satan? And then this, I've heard about this problem before. I don't know whether it's known. Maybe someone here knows. I decided to put it up anyway. So there's in this paper about Bensis and Vigderson, short proofs are narrow. He has a way. They show a way of given a small proof, constructing a proof that has small width. Okay? But when they do this width reduction, the depth blows up. So the depth becomes supercritical. So is this blow up necessary? So what is the width depth relation that you should get for Bensis and Vigderson? I don't know if this is also, I'll leave it there. And another recent result, which I find really nice. So there's this proof system, which is resolution over parity of literals. And we don't know how to prove lower bounds for this system. It's one of the frontiers just above what we can do. But there's a recent result where it was exponential size lower bounds were shown for res parity for depth up to n times log. So if supercritical trade-offs did not exist, this would have solved the problem, but they might exist. So can we actually separate res parity from depth n times log n res parity? So I think that's also. Okay. Thank you.
Yeah, could you just, there's a result of Gray and Newman, which you were mentioning about, there was a result of Gray and
Huh?
which you were mentioning about. Could you just elaborate on that? Because I was just looking it up, it was in the context of C5 graphs. And in context of the cycle graphs.
Yes,
Right.
yes.
So what result of that, is playing a role in your results?
Right, that's a good question. Yes, these cop robber games,
Yes.
you can get also some connection with these with these graphs when you want to distinguish whether two graphs are isomorphic. So there is a connection there, and so it's from this cop robbers to the bispecific limit algorithm. Now, there is also the connection between the cop robber games and resolution with depth. So that we use this connection for with depth, but you can also have this result. And what their result is, so this kind of construction of condensing was their construction. We just had to generalize it. And what they got was precisely when you have dimension k, you require this many rounds, and with dimension k plus 1, you can do it in fewer rounds. So it was like between k and k plus 1. And what we needed was between k and k times 1 plus epsilon, or k times 2 minus epsilon. So we needed like a larger gap there. So that was the difference between the two results. Is that? Yeah. Yeah.
Separating Reslin and depth n log n Reslin and supercritical trade-off. What was the connection between?
So if supercritical trade-offs did not exist, then we could always reduce the depth without blowing up the size. And in that case, an exponential lower bound for depth n would already be the exponential lower bound for any depth. But I expect there to be supercritical trade-offs here too. So yeah, can we show this? Can we show a separation there?
Take to wrestling, that would answer the last question.
Exactly. Yeah. Yeah.
Where is your paper?
This paper, it's on archive. Yeah.
Any other questions?